under Professor Arthur. Today I'll be talking about correlations in continuous multi-species TIFR, and we'll be proving a conjecture that is posed by Eric Ars and Swante Linusson. The layout of the talk is as follows. We'll introduce the model, then we'll define multi-species TIFR. We'll delve into some preliminaries that are used to solve the conjecture, and then we'll come to the main results and show the proofs. First introduction. Now, exclusion processes are a class of interacting particle systems. In particular, totally asymmetric exclusion processes, or TASIPs, are one class of exclusion processes. We'll see them in detail in a little while. Now, TASIPs are of interest to various fields of mathematics like probability, representation theory, and so on, because of their connections to objects like n-core partitions, Y groups, and McDonald polynomials, and so on. We are in particular interested in the stationary distribution of the TASIP, and in that as also on the 2-point correlations. Now, some background of the problem. Frank Spitzer in 1970 studied the phenomena of interacting particle systems and gave many models of such interacting particle systems. Then Ferrari and Martin in 2007 studied a Markov process on multiline queues and showed the connection to multi-species TIFR with these processes. Then Lam in 2015 studied infinite random reduced words in affine while groups, and he conjectured a formula for the limiting direction of random walks in these groups in terms of a Markov chain on a set of permutation. And in 2017, Iyer and Linusson realized the connection between the multi-species TIFR that Ferrari and Martin studied and proved a stationary distribution for with the Markov process that Lam had found the formula in terms of. And in they studied correlations in the stationary distribution of multi-species TIFR, and in that process, they proved the conjecture that was posed by Lam. Ars and Linusson studied a limit of the distribution studied by Iyer and Linusson, and that distribution can be seen as a limit of the stationary distribution of multi-species TIFR on a ring with finite sides. And while studying that, they conjectured an explicit formula for the 2-point correlations of adjacent particles in the multi-species TIFR on a ring. We will go on to prove their conjecture in this talk. So now let's define what multi-species TIFR are. So, before that, we give some general framework. Multi-species TIFR is, as I said before, is a class of interacting particle systems where the particles hop from one side to another on a ring. The particles are of different species, and the ring has finite number of sides, and each side can have at most one particle. This is where the term exclusion comes from, as there can be at most one particle on each side. Some of the sides can be empty as well. We are interested in the stationary distribution of the process. And
why is the word ring highlighted? Is
that it's to show that the model, the transitions are on a ring, and
ring means
it's a circle with finite number of sides for now. Then continuous multi-species TIFR arise as we take a limit of the stationary distribution of multi-species TIFR on a ring. We'll see this in detail just now. So first we define multi-species TIFR. We take a ring with L sides, L being finite. Now for a tuple M, a multi-species TIFR of type M has M1 plus up to Mn sides of the ring occupied by particles. So out of L sides, these many sides are occupied by particles, and remaining are empty. Now each particle is assigned a label from the set 1 up to n, and the labeling is done in such a way that there are exactly mk particles with label k. The unoccupied sites are also labeled, and the label chosen for them is the highest of them all. We'll see the reason why we do so.
Sorry, n is what?
N is the number of species. So each species has, so a species I has mi particles. And the unoccupied sites are labeled n plus 1, so that the label of an unoccupied site is higher than the label of any particle. So for an example, this is a ring with 6 sites. 2 of the sites are unoccupied. The remaining 4 sites have some labels. And so, for example, the label I and J are also there. So we will use these labels to define the dynamics of the process. So now each particle carries an exponential clock which rings with rate 1. Whenever the clock rings, the particle, say which has label I, tries to jump on its left. This jump is successful and the particles exchange positions if the particle on the left, which is J here, has a label higher than I. Or it is also possible that the site on the left is unoccupied, which we can say has the label n plus 1, which is higher than I. Then as well, the particle at I jumps to its left.
So it's not clear to M1, M2, Mn is what? It's the
These are positive integers. For
it indicates what?
it indicates number of particles which has the label I. So in this particular example, M1 is 1. Yeah.
I mean, is it one for? I mean, at each side there is most one particle.
Yes.
So this does not actually tell you the configuration.
No, it just says that.
Consider the set of consider all possible configurations, whether M1 ones, the remaining plus one. So there's some multinomial coefficient and
Is the parameter?
yes.
So you are thinking of the model as having actually n plus 1 labels, and
Yes.
each site is being assigned one of them.
Yes, we can see it that way. Yes. Okay, I'll move on. So so this is the dynamics of the process, and this Markov process is irreducible and aperiodic, which thus has a unique stationary distribution. Now,
So if it is occupied and the label is less, then it stays on the sorry.
yes, the jump does not happen. Okay, now we'll see for one particular m, which is the unit vector, 1 repeated n times. For this particular m, let the stationary distribution be denoted by pi L, where L is the number of sites on the ring.
So Markov process. You are
Yes.
looking at M1 to Mn as Markov process.
No, so the ring has configurations where the particles are spread different way.
Okay.
The transitions can happen,
Okay.
which take it from one configuration to another.
Okay.
Now
so
this-
the space is the space of all configurations on a ring.
Yes,
Label configurations on a ring.
yes, yes.
Because the dynamics does not change the number of species.
Number of, okay. The
It-
label is always fixed.
Yeah, it just switches the position of the particles. So this process defines a unique, defines a Markov process, which has a unique stationary distribution. In particular, for M to be the vector where each mi is 1, let the stationary distribution be denoted by pi L, where L is the number of sites on the finite ring. Now we take the limit as this L tends to infinity while keeping the M constant. So in effect, the number of particles are remaining fixed, and the site becomes, and the ring with finite sites become a continuous ring, also known as S1. We call this limiting distribution as pi infinity, and this distribution is known as is said to be continuous multispecies Tasip on a ring. This terminology was given by Aas and Lemma. Note that pi infinity, which is the limit of a stationary distribution, is a distribution. It's not shown to be a stationary distribution of any Markov chain yet. And let Cij denote the probability that particles of species I and j are adjacent to each other in this distribution pi infinity.
So there are n particles on the circle at real positions. It's a description of
Now, Ars and Linusson gave a conjecture on thisCijn for different cases
So
by
limit
ordering.
existing is not an issue. Actually, it's very interesting.
No, the
Limit you can always-
Ye- yes, the limit exists. It's not shown to be a it's not shown to be a stationary distribution.
yeah, no, it's not trivial.
That it's a probability distribution.
Yes.
Can you go back to the previous slide, please?
Yes.
N tends to infinity and
The L tends to infinity.
M does not.
No, the M remains fixed. So the number of particles that are on the ring are fixed. With
The number of holes is infinite. There's only one particle of each. One.
so this is a distribution of labeled particles on a ring where each label appears exactly once. Yeah, so Ars and Linusson gave the conjecture on this Cijn, which is the probability that I and j appear adjacent to each other on this ring.
No, it's not adjacent. One follows the other. If they are adjacent, then it will not have different cases.
It's the probability that I and j are adjacent, with I being on left of j. It's split into 4 cases depending on the orders of I and j with respect to n as well. So we'll prove this result in the coming slides. But
Sorry, this is for m equal to 1 to the n,
yes,
and one can always reduce to that case, is it?
yes, it can be done by lumping, but I don't think it's done yet. The conjecture is given for 1 raised to the power n. So we'll see some preliminaries, some tools we need to prove this result. So one of them being multiline queues. Now, a multiline queue of type M, again the same vector, is a collection of n rings with L sides each. These rings are same as the circles with finite number of sides. For ease, we'll see them as rows here. Now, in IIT,
Sorry for
Yes.
slowing you down.
no, it's all right.
It's only good for all of us. But, so this thing, n, I mean, when n is 2 or 3 or something, there is, you know the full distribution or not? This was partial information, right? Conjecture. But
Yes.
things, n equals to probably this gives, I don't know.
N equals to it's uniform.
It's uniform.
So there are 2 particles on the
Oh,
circle,
no.
2 particles on a circle, which you have exact full distribution or something. There are only 2 particles on a circle.
On a
right?
circle. Yes.
So
Yes.
if it's described,
Yeah, this is this.
Yes.
You mean on this one?
yeah.
Yeah.
So I
Pi
mean,
L itself, what he's asking.
You're asking about
pi
pi-
infinity. Say this is partial information on pi infinity, right?
Yes.
So I'm asking for small n, you have the full understanding of the distribution.
Yes, for n equal to 2, it can be seen as one particle in one hole in the discrete case, and then that is
No,
known.
the continuous system. We're talking about the
Continuous
case.
case.
N equals 2.
And it's
So
Yes.
there's 1, 1 and 1.
1, 2. Okay.
So by translation invariance, you fix the position of 1 as the origin. The other one is
the
continuous.
density of will have some density.
And that way.
They have to.
But it's not uniform. Or
No.
No.
Yes. Because
Yes.
I'm not sure I'm following. So when we take limit that goes infinity, you're increasing the number of sides.
Yes.
So the configuration, is it that the sides are like spaced and then you're taking the
No, so effectively, I'm increasing the unoccupied sites because the M is fixed, and M is giving me the configuration of particles with their
He's asking
multiplicity.
something. No, you are taking a scale limit. So you have a thing, you make the spacing between the sides. And then limit to that.
yeah, but so they have the same space. The length of each side is the same every time.
Yes.
Because it's a graph.
Groups of
Then it's finite, then it's just a graph. You do whatever, but it's mostly.
Okay, now, so a multiline queue is a collection of these n rings with n sides each. Here, there is no species of particles. It's the sides are either occupied or unoccupied. We define some variables capital Mi as the sum of first I mi's, and multiline queue. The particles are occupied in this way, in the sense in ith row, capital Mi of the sides are occupied by particles, and L minus Mi sides are unoccupied. Hence, because capital Mi's are increasing, the number of particles that are occupied in each row increase as we go down from top. So this particular example is a multiline queue of type 2122.
Can you use the point?
Yeah, this
You can't see.
this example is a multiline queue.
You're pointing up there.
Maybe you can point on the computer, then the online people can also see.
Then use the
Okay.
pointer on the.
But it's not translating. Okay. Okay, so yeah, so the this particular example is a multiline queue of type 2122. Therefore, 2, 3, 5, and 7 of the sites are occupied in each row respectively. Now, Ferrari and Martin studied a Markov process on these structures. Each row has to be thought of as a yes, it's a ring.
It's a discrete cylinder.
Yeah.
Yes. Yeah, so Ferrari and Martin studied a Markov process on these multiline queues by defining transitions between them, and they found the stationary distribution of this process, and they proved that this distribution is uniform.
Why did they study this?
Because the stationary distribution of this process can be seen as a function of the stationary distribution of multi-species Dasip of type M, where this M and that M is same.
It's not stationary distribution. This process that they invented lumps as a Markov process to the multi-species. So no, there is a lumping. There's an algorithm. So Nimisha is going to explain it.
Yeah,
But the idea is that from these things you get a single configuration with M1 ones, M2 twos, and so on. There's an algorithm. That because the stationary distribution of this process is uniform, to find the stationary distribution of this process, count the number of queues that project.
Yeah, I'll go over them in a while. So this was multiline queues for a discrete case. Now we can see continuous multiline queues. Continuous multiline queue of type M again is a collection of n copies of S1. Now S1 is the continuous ring. Each ring, each of the copy of S1 has again Mi particles in ith row from top. Mi is defined similarly as before, as the sum of first I small mi's. Also, let's denote capital N as the sum of all the mi's. So in this example, we have 4 copies of S1, and again it's S1, but I'm writing it as a straight row. Now each of the row have a few particles on it. Ignore the labels for now. So now this is a continuous multiline queue of type 1312 because there are 1, 4, 5, and 7 particles in each row respectively. The total number of particles here are 17, so that makes capital N equal to 17. Now the labels of the particles are assigned in such a way that they show the ordering of horizontal position of each particle as seen from left to right. So we have 1 here, then we have 2, 3, and so on.
This capital N is
is the
Sum of all the little m.
all the big MIs.
Capital M. But MI, capital MI is sum of the
Little MIs. First I little MIs. So yeah, because the particles increase progressively in each row, capital N gives the total number of particles in a continuous multiline queue. Now these labels are interesting in the sense because Ars and Linnaeus gave an equivalent integer representation of these multiline queues in terms of triangular array, which they called as placements. So to see how to get there, first consider a multiline queue with the labels. Just focus on the labels and remove the queue and the particles. If we left align these labels, we get a triangular array. And so it's equivalent to study these integer arrays, these triangular arrays, to study the distribution of continuous multiline queue.
Not the whole multiline, it's just to get the relative positions. If you want to know the distribution, want to know the precise locations, this is not.
Yes, but
you just want to know the positions.
because we need them for the correlations, it's enough to see the relative ordering, and hence triangular arrays suffice.
When multiline queue, there was some intervention condition.
Sorry, what condition?
I mean, so otherwise, even relative positions, I don't think that. So first row to second row.
No, there is no. This is a random.
Sure, but are they? I mean,
so go back to the. So here, the stationary distribution is uniform.
no, stationary distribution is fine, but the configuration.
Yeah.
Is it all possible configurations?
Satisfying
Everything
this
is
condition. So
just that number of particles in each row is fixed, but there is no other.
No.
So here also all possible arrangements are.
It's just that the vector mi remains constant.
Then what is it that you did by
Yeah.
aligning? Yeah.
Okay, so because I'm only concerned with the relative position of each particle, I'm reducing this continuous multiline queue into a triangular array, which preserves the information that we need. So I'm just considering the labels and then left aligning them to get a triangular array where the number of integers in each row is capital Mi. Okay.
No, not.
Now we show the lumping that Sir has said. So we define an algorithm called bully path projection, which projects a continuous multiline queue, here a triangular array, to a word. Now, to see this, we bully path projection constructs bully paths, which are paths that go from top to bottom, hitting each row exactly once. So we start with the top row, and we have 5 there. We look for an integer in the second row, which is larger than 5, but the smallest one in being so. So 5 hits 7, because 7 is the smallest integer that is bigger than 5. Then 7 looks for an integer to hit, and it's hit 8. And then 8 goes on to hit 11. By hit, I can also say bully. And then 11 is then labeled as 1, because the bully path that ends at 11 begin in row first. Now we repeat the same process with the remaining integers in second row. So 1 bullies 10, which bullies 12, and then 12 is labeled as 2. Similarly, 3 and 9 also start their bully paths and end at 14 and 17 respectively. So these are labeled as 2. So now second row is done as well. Third row has only 16 left. 16 does not have anything larger than itself to bully in the last row. So 16 wraps around to the fourth row and hits the first available particle, which is 2. This wrapping around is special, and we'll see what its purpose is there. So, but we denote it as 16 wraps around and bullies 2, and we write a W over the path. Now in the fourth row, there are 4 and 6 left, which are not bullied. So we write 4, we label them as 4. The resulting word 3, 4, 4, 1, 2, 2, 2 is the projected word of the continuous multiline queue that we began.
The number of eyes is small.
Yes. This triangular array was of type 1, 3, 1, 2, which is the multiplicities of 1, 2, 3, 4, respectively. I'll go back.
3 is M1. No.
No.
M1 is 1.
M1 is 1.
Oh, yeah, I see. M2 is 3.
Yes.
And 3 is 1.
One.
And 4 is 2.
Yeah, these are the little m's.
Because the first one took M1 when you start from the first row, you take M1 guys.
Yes.
In each row. And then the second row guys, it starts to take M2 from the first.
So now we, if M was the kind.
When did this kind of algorithm?
But this is what I'm saying. This is Ferrari inverted algorithm essentially. So for the discrete case, if you take that. So can you go back to the discrete example?
Sorry.
This one. So first row, there are 2 particles, right? So you can explain.
Yeah, so the first particle in first row bullies the particle directly below it. And that one will go on to bully the second particle here. And this will go to bully this.
And you put a 1 over there.
Put a 1 over here. So it just goes down and right until it sees a particle. Now the bully part by integers is mimicking the same process because it's just the ordering. So from first row to because there are 2 particles. In the last row, 2 of the particles are labeled as 1. And from second row, only 1 will be left, which will start a new bully path. And in the final row, 1 of the particle will be labeled as 2. And so for 2 particles will be labeled 3, and the remaining 2 will be labeled 4, giving the 2, 1, 2, 2 here.
You're trying to jump to the left, right? Is that correct?
No, it goes down and goes right. Goes down and goes right.
In the original model, the jumping is to the left or right?
Oh, in the tacit, it's to the right. I mean, so it's a ring. From inside it sees as left. From outside it can see it as right.
Oh,
It's
so you're
that.
the way you're going is right.
Yes.
Trying to jump to the right and that's
Yes, that's the bully. So now omega is denoted as the projected word of M, and by the paper of Ferrari and Martin, we have seen that the projected word omega has the same distribution as the continuous multispecies classic of type M. They worked on discrete case, and we can take the same limits to show that the result holds here as well.
What was the dynamics for this multiline thing? Did you describe it?
No, I didn't describe it here. Yeah.
No, there is no that.
For the discrete case,
For the discrete case,
there is one.
Discrete.
Yes.
It's a bit complicated. It's again the particles exchange position if there is something on the left in each row progressively, but it's complicated to describe now. Okay. Yeah, so the projected word, which is the labels of the last row after the bully path is done, has the same distribution as the continuous multispecies TASIC of type M. And since that distribution, the latter distribution is uniform, it is enough to count the number of continuous multiline queues that project to omega to find the distribution of omega.
This is the continuous stationary part of the inverse, right?
Yeah.
The projection is the continuous multi-species except the stationary
Measure.
It's
Pi infinity.
pi infinity.
Yeah, pi infinity.
Yeah.
Out of place.
We don't have a process.
It's, yeah. So now,
Each omega is basically one.
How many ways we can get that?
from the multiline queues, because we know the distribution for those. Yeah, so it is enough to look at the class of continuous multiline queues that project to a same projected word omega. Now we define an operator in that class. So if M and M dash are two continuous multiline queues, yes, yeah, okay, M and M dash are two placements of same type, then if the operator S acts on M and gives M dash, then M dash can be seen as obtained from M by adding one mod N to each entry of M. And then if needed, we can arrange any row in increasing order if the order is disturbed. We'll see an example. So on the left, we have a running example. By operating it by S, we see that each entry is increased by 1, except for 17, which is the highest entry. 17 now becomes 1, and then the increasing order of the last row is not there. So we rotate the last row so that 1 comes in front of the last row. So 2, 4, 6, 11, so forth becomes 3, 5, 7, 12. And 17 becomes 1, which comes in the front of the last row. So this example motivates a result we'll see in a while. So if M and M dash are two placements which are related by shifting operator, their projected words are also related by this lemma. So like we saw, if N, which is the largest entry, it's in the last row of M, then omega dash is obtained by rotating omega 1 position to the right. And if N is in a row above, then the projected words are same. Because omega is obtained by labels of the last row. Next, we see a principle. So to all, okay, so in a TASIP, for a particle labeled I, all the particles which are labeled lesser than I look the same, as do all the particles higher than I. Using that principle, we can, so if we have M as 1 to the power N, we can bunch the ones in two different classes. So first S1s, I'm bunching first one S1s together, the next T1s together, and the remaining as well. Then this is what I'm doing here is lumping a continuous multi-species TASIP of type 1 to the power N to another multi-species TASIP of type MST, which has S1s, T2s, and N minus S minus T3s. So the first S1s become a 1, the next T1s become a 2, and the remaining ones become a 3. In doing so, now I'm doing this to find an expression for Cijn, which is the probability that I is followed by a j in the multi-species TASIP, continuous multi-species TASIP. So, so by bunching, a continuous multi-species TASIP of type M can be projected to many continuous multi-species TASIP of type MST, where S and T are such that J lie in the second bunch. So J is greater than S and less than S plus T. And I lie in the third bunch because I is greater than S plus T and less than N. So therefore, to study the correlation Cij, we can study the correlation, or we can study the probability that 3 is followed by a 2 in the multi-species TASIP of type MST for each of the possible ranges for S and T.
Some basic things.
Yes.
So in the 1 to the N case, nothing overtakes nothing. Is that I mean?
Overtakes?
Jumps in
No.
So which way? That's what I thought.
If
Is it the lower?
uh, I jump, I
Oh, sorry.
jump.
Which one overtakes? Sorry, no. Which one overtakes? Higher one overtakes lower one. So
Lower one, if lower one is on the right and higher one is on the left, they exchange positions. Yeah, so in place of studying multi-species TASIP of type,
So the population basically and the bulk behavior, the entries of a certain type, it doesn't matter which type they are. So the higher will all look the same and lower will all look the same.
yes.
If you are looking at only one type I, it has a fairness sequence.
Yes, it reduces to a 3-species TASIP. Now we define T greater of ST as the correlation that 3 is followed by a 2 in the 3-species TASIP.
3 or 2? I was thinking
Because I'm taking this for the case I greater than J, and I have taken SNT such that I lies in the third bunch and J lie in the second bunch. So Cij can be written in terms of T, where 3 is followed by a 2 in the 3-species TASIP. It's a double summation where I and J run in their respective ranges. Now I define a quantity called simple T greater of ST as take M to be a continuous multiline Q of 3-species type, and omega to be the projected word of M, such that N, the highest entry, is in the last row, and the projected words have 3 and 2 in the first and second places. Till now, we were only concerned that 3 and 2 were adjacent to each other, with 2 followed by a 3. I'm taking a special case where 3 is first and 2 is second. And by fixing N to be in the last place, I can show that the total probability can be expressed as N plus 2S plus T times T greater of ST. Skipping the proof here, but this can be seen by the lemma which relates the projected word of shifted multiline Qs. The script T is the correlation that 3 is followed by a 2 anywhere on the ring. And this is for first 2 positions with the added condition that N is in the last row. Now, using this lemma and principle of inclusion-exclusion, I can write Cij in terms of T greater of these quantities. Similar analysis can be done for the case I less than J. And if I define T less of ST as probability that first and second positions are 2 and 3 respectively, then Cij for I less than J can be expressed similarly. So we need these 2 equations. And if we are able to compute T greater of ST and T lesser of ST, then we are done with solving the conjecture. So yeah, another thing we need to do our analysis is standard Young tableaus. So I'll give some basic definitions. So first, a partition of N is a tuple lambda. Yes.
So even though the original conjecture was for only one particle of each type,
Yes.
now that you need to compute probability even in the 3 species when there are particles of
Yes.
each type, there are many particles.
Yes, but
In
because
effect, you have to do this computation.
yes, but because there are 3 species, the analysis is doable by hand.
This height of the placements is
Yeah, so we can characterize the bully parts in an easier way. So yeah, a partition of N is a tuple of strictly decreasing non-negative integers. Yeah, sorry, weakly decreasing non-negative integers such that N is the sum of all lambda i's. A Young diagram of lambda is a drawing which has lambda I boxes in ith row, and the boxes are left justified in the figure on the left. That shows a Young diagram of shape F531. Then a standard Young tableau is the filling of such a Young diagram with integers from 1 to n such that the entries increase strictly as you go from left to right and top to bottom. So on the right, we show an example of a standard Young tableau, which of shape, which is a partition of 9. Now the number of standard Young tableaus of a fixed shape lambda is denoted by f lambda, and it counted using hook length formula, which is f lambda is equals to n factorial divided by the product of HAs. HA is the hook length of the box A, which is the number of boxes on the right of A and below A, including that box itself. So I take the hook length for each of the box. I multiply all the hook lengths together and I divide n factorial by this product to get the number of standard Young tableaus of lambda. Okay. Now there is where we use standard Young tableaus is clear by this lemma. So the set of continuous multiline queues or placements of type M, which have no wrapping from either of the row under the Boolean projection, is in bisection with standard Young tableau of shape lambda, where lambda I is mi is written in reverse order because lambda i's are weakly decreasing. So, so to see this proof, consider a placement where ai, bi, ci are integers from the set 1 to capital N. Now, because there is no wrapping, as has to be less than bs plus t. As minus 1 is less than bs plus t minus 1, because each of the ai should find something below them to bully, and so on. So we have the set of inequalities as minus I less than bs plus t minus I. Similarly, there is no wrapping from second row to third row, which gives us set of inequalities bs plus t minus I is less than
Wrapping means you can always find someone
in the next
Which is larger than.
which is larger than that. Now these inequalities combined with the strictly increasing property of each row gives us this set of inequalities. Now this this configuration rotated by 180 degree in itself gives a standard Young tab. It gives a Young partition. It gives a partition of shape lambda, where lambda is the capital Mi is written in decreasing order, and the explicit bisection is given by this function Yij, where Yij is the integer in the box in ith row and jth column to be capital N minus Mij plus 1. So by this bijection, we can say that the number of multiline queues with no wrapping is same as f lambda. We will use this lemma quite a few times in the proof. So yeah, now we'll state the main results. So these are the two main results we have proved, where it's the conjecture of ours and Linison is split into two cases. First for I and j, and then I greater than j, and second for I less than j. So first we proved theorem 4.1, which is the correlation for the case I greater than j. Now, first we consider the set SST to be the multiline queues of 3 species where the projected word begins with a 3 and a 2. And let tau st be the cardinality of this set. So SST contains placements which look like this. And the projected word has 3 and 2 in the first two places. We characterize the multiline queues that are in this set with the help of following lemma. So a placement belongs to this set if and only if the following conditions hold. A1, if any A1 bullies BK, then BK has to be greater than C2. C1 and C2 take the values 1 and 2 respectively, and there is no wrapping from either first row to second row or to second row to third row. So I'll say the proof in few short lines. Let M be in that set and suppose A1 bullies BK. Now if BK is less than C2, the bully part that has started at A1 ends either at C1 or C2, because BK will bully either of them, and we will get a 1 in place of omega 1 or in place of omega 2, which is a contradiction. So that means BK has to be greater than C2. Now, if there is similarly, if there is any wrapping from second row to third row, it makes sure that C1 gets bullied either by wrapping or it has already been bullied beforehand, which is again a contradiction because we want omega 1 to be 3. That means we want C1 to be never bullied at all. Now, but we want omega 2 to be 2. That means we want C2 to be bullied by some BI, which is not bullied by any A. To make sure that happens, then B1 has to bully C2, and B1 cannot be bullied by any AI, which fixes the inequalities to be C1 less than B1 less than C2, and B1 is less than A1. By this increasing property of the rows, we can see that C1 has to be 1 and B1 will be 2. Now, the third and final condition is that if there is any wrapping from first row to second row, that means some of the AI will bully B1 and B1 bullying C2, which again contradicts. So this proves the 3 conditions. The reverse implications are straightforward to see. Now, using this lemma, we count the number of multiline queues in the set SSD, or we count tau ST. So condition 3, which said that there is no wrapping from any of the 2 rows, it implies that Cn is n, that is n is in the last row, because if n is in any other row above, wrapping has to happen. Now, so if there is any bully path which is starting in first row, it has to end beyond C2. That means if any BL is bullied by some AM, then BL should be bigger than C2, otherwise C2 will get bullied. So this property tells me that there are at least S BIs bigger than C2 because they are S bully paths starting in first row. That restricts the number of integers that restricts the number of C2 values C2 can take to be in this set, because 1 and 2 are already assigned. C2 can be from 3 up to S plus T plus 2. Higher than this will make it impossible for C2 to not be bullied by some path starting in first row. So let me assign I to C2 and let A1 bully BK. Then BK is greater than C2, as we have seen earlier. Also, since A1 is bullying BK, BK minus 1 is less than A1, which is less than BK. Therefore, all the numbers between 3 to I minus 1 have to be assigned first to the remaining BIs, and then the remaining 2 will go above to A1s, because A1 in itself is bigger than BK minus 1. So 3 to I minus 1 are assigned to B2 up to I minus K minus 1 in one particular order. After having assigned all of these entries, this assignment leads us to the range of K, which I'll skip here, but we can see that K lies between 2 and T plus 1. Now the remaining entries have no wrapping in them, so we can see a bijection between the remaining configuration and standard Young tableau of shape lambda ik, where lambda ik is the length of remaining entries. So, so this gives us tau st as the double summation of f lambda ik, where k ranges from this and I goes from 3 to s plus c plus 2. Having been able to compute tau st is the number of such multiline queues. This can be simplified to this expression, and now putting tau st back into the probability t greater of st, we have an expression for T. And now using the equation we got from principle of inclusion exclusion, we can put it back to get Cij for I greater than j case. This proves our first result of theorem 4.1. And now we move on to the next result. So, sorry, 5 minutes. Okay, I'll move fast. Okay, now for I less than j case, we define similarly the set of multiline cues which project to the desired word, and theta st as the cardinality of that set. Now in place of 2 and 3, first we take arbitrary x and y's, and we denote the number of multiline cues that project to word beginning with x and y as nxystn, and note that theta, the required quantity, is n23. Also, let nzstn be the number of placements that project to word beginning with z in the first place. So by these definitions, we have n13 plus n23 plus n33 equal to n3. So in the similar line of proofs for what we have done earlier, it is easy to show that n33 can be seen as a product of binomial coefficient and a Hoekland formula. Similarly, n3 is computed similarly and simplified to written like this. Now this equation says that having found n33 and 3, to find n23, it is enough to compute n13. We also have an expression for that, and having lemma 4.4 and 4.5, we can compute n23 in terms of the known quantities, which when put back into the probability expression, this completes the proof of theorem 4.2, the second major result of our talk for the case I less than j, on the condition that theorem 4.5 holds. So the proof of theorem 4.5 takes a slightly different approach to what we have seen till now. So we have this configuration where the projected word has 1 and 3 in first and second place, and the largest entry n lies in the last row. Now, for having omega 2 to be 3, we can see that if there is any wrapping from second row to third row, there can be at most one such wrapping. Because if there's more than one, then C2 will be bullied, and we will not get 3 in this. Now, these configurations can be divided into two types, where there is no wrapping at all, and when there is exactly one wrapping. And in that case, BS plus T wraps around and bullies C1. We enumerate these two cases separately and let the numbers be denoted by alpha 13 and beta 13. So first we characterize alpha 13. So the number of placements that project to 13 with no wrapping have to satisfy these two conditions. They can be seen similar to the characterization we saw earlier. So I'm skipping the proof here. And using this characterization, the number of alpha 13 can be computed to with this quantity. This is again a product of a difference of binomial coefficient and a Hoekland formula. This theme appears a lot in this paper, in this result. So it's interesting to note. I'm skipping the proof again. Now we will characterize the second class of placements that project to 13, where there is exactly one wrapping from second row to third row. There is a characterization here, but using this characterization, it is not straightforward to find a formula like we did earlier. So yeah, recall that this number is counted by beta 13. Using some simulations we saw for different values of STN. These are the values for beta 13. And having found the patterns, we could see that beta 13 satisfies this expression, which once again is a product of binomial coefficient and a Hoekland formula. Now this expression satisfies a recurrence relation instead. Beta 13 STN is the sum of beta 13 for S minus 1, T plus 1n, S T minus 1n, and S T n minus 1. Each of the terms on the right hand side count number of multiline cues with one less entry in each row respectively. And that's where the proof of this recurrence relation also comes from. I'll skip the proof here. But the interesting thing to see here is this recurrence relation 9 is also satisfied by alpha 1 3 because they have the similar structure as a product of binomial and a Hookland formula. Now n13 being sum of alpha 13 and beta 13 is bound to satisfy the same recurrence relation. We had an expression for n13. Let me denote it by PSTN for now. And by using Pascal's identity and properties of Hookland formula, I can show that PST satisfies the recurrence as well. So all we are left to show is that N13 and PSTN should have the same initial conditions. This is easy to see for n equal to s plus t, and for s equal to 1, the initial conditions are same. So what we are left with is the initial condition for t equal to 1. So proving n13, s1n, sp, s1n will complete the proof of theorem 4.5 and will complete the main result of this talk. So for that we have a proposition. I'll just give a short sketch of the proof. Okay, sure. So, okay, this just involves lumping of a 3-species tacit to a 2-species tacit, and then the 2-species tacit is fully solved. So we use those equations to find a value for n13. That ends the proof. These are the references.